All right, so in this video we're going to talk about electron configurations. Hopefully you remember how to do electron configurations and orbital notations, but we're going to go through and do some review. We'll go back and cover all of this. So we're going to start with looking at the periodic table. Most of the times you'll see it will look like this. However, it really should look like this, broken down by blocks, right, with the F block there in between the D and the S and the D block instead of way down at the bottom. And helium really should be over there in the S block, all that good stuff. And if we break it down even further, right, we can even look at it like this, where we look at the way in which the electrons fill up, right? You've got like your 1s, you've got your 2s and 2p, 3s and 3p, 4s, but we come here, 3d, 5s, 6s, and again, right, 4f. And when we go to talk about quantum numbers, why we have 3d and 4f as the first d's and f will make more sense if you're watching this after the quantum numbers, or if you come back to this, right? If we have n as our energy level, right, and L as our subshell, right? Because L can have values of 0 through n minus 1, right? If you have n equals 3, right, that would be 0 through 3 minus 1, or 2, right? And since for L, 0 is S, 1 is P, 2 is D, 3 is F, right? That means that the third energy level is the first energy level that can have a D subshell, right? Just like n equals 4, fourth energy level, 0 through n minus 1, or 4 minus 1, so 0 through 3, which means the fourth energy level is the first energy level that has F available, right? Because n equals 2, that's 0 through 1. For anything 2 or 1, right, D and F are not available. So if you're watching this after the quantum numbers video, that'll make sense. If not, it'll make sense when you watch the quantum numbers video. But that is the actual explanation of why the third energy level is the first with a D subshell, and the fourth energy level is the first with an F subshell, and why those are not 4D starting and 6F starting. So there you go. Okay, electron configurations. Hopefully you kind of remember this. We have energy level, subshell, number of electrons, and then we'll talk about those other two things in a second, right? Your standard electron configurations look like this. They have a whole bunch of things in a row that look like this, that have the parts, right? We're talking energy level, and for that you can think the row on the periodic table. They have the subshell. For that you can think what block is it in on the periodic table, and then number of electrons, and for that try to remember count in from the left edge of the block. And then some terms you should be familiar with for this one: the Aufbau principle. It means the building up principle, and basically it just means that electrons fill lower energy levels first before filling anything higher, right? So that means every electron configuration starts with 1s and works its way up from there. Now, the other term that you should be familiar with, but I will say it here just to remind you of it, valence electrons, the outermost electrons, or you can think about it as the electrons in the highest numbered energy level when you're looking at the electron configuration. All right, so remember that highest numbered energy level, all the electrons in that highest energy level. So when we do our examples, I will point out the valence electrons. So for doing electron configuration, we need to remember that subshells have orbitals, and that each type of subshell can hold a maximum of a certain number of electrons, right? So S holds a maximum of 2, P can hold a maximum of 6 electrons, D 10 electrons, F 14 electrons. So here is one version of that great diagonal arrow chart showing you the order that everything fills in, right? We start with 1s, then 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, so on and so on. You can see it here. Here's another representation of it. I don't know if this makes it any easier on this side. Oops, I don't know why I just did that. On this side over here, right, it's showing from bottom to top. That was a great straight line. Bottom to top, what order they fill in, right? So all the way from your 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, right? And you can follow the line over here on the right. It's like some sort of crazy board game. But those are various ways that you can represent how these things fill. However, if you just take a look at your periodic table, electrons fill from left to right, top to bottom. That's all there is. So an example, or 2, or 10, maybe. The first one we'll look at, which is one of my favorites for any kind of example, carbon. So if you look on the periodic table, right, you find carbon up there. If you don't see it, it's in the P block, right in the second energy level there, 2 in from the side of the block. So we're going to start 1s. The 1s is full. 1s2. Then comes 2s. 2s is full. And then 2p. And you count in from the side of the block, 1, 2. And so you have 2p electrons. So here let's take a look at valence electrons. Now for this one, right, these are going to be the valence electrons because they're both in the second energy level, right? Highest numbered energy level. So carbon has 4 valence electrons, right? 2 here, 2 here. Easy enough. So then let's take a look at polonium, way down there. Now, for anything beyond about fluorine on the periodic table, I usually like to look at the last term of the electron configuration and then just know that everything before that is filled in. So if we look at polonium, right, we're going to look for what block it's in, P block. We're going to look what P, so it is in 6P, and then we're going to count in from the side, 1, 2, 3, 4, and so we know the last term in the electron configuration for polonium is 6p4. And then we just fill in, using one of those charts, or looking at the periodic table, everything that comes before it, which would be all of this. Right? And before we talk about anything else, we can take a look at the valence electrons here. So for this, we find the highest numbered energy level, 6. We count 2 and 4, which is 6. So polonium has 6 valence electrons. Now, I know right now you're looking at this and you're saying, I don't want to write all that. And if that was your first thought, then you would make a great chemist, because no chemist wants to write all that. So they came up with a shorthand for doing this, which, if you remember, is the noble gas core configuration. So what we do is we look and we find where the last noble gas would be, right? It ends in something P6. So that's the last P6 in the electron configuration. And we find what noble gas corresponds to 5p6. And we write it like this. Turns out xenon ends in 5p6. So then we have xenon, and then everything here that is not in the electron configuration of xenon. And that is how you write a noble gas core electron configuration. Hopefully you remember that. So the other thing with electron configurations, we can look at something called isoelectronic atoms. And isoelectronic is when two atoms, neutral or ions, have the same electron configuration, right? That means they are isoelectronic. Now for this, right, this is neon's electron configuration. But then we have a nitride ion, right, -3, which means that we have added 3 electrons to this, right? Because if we have neutral nitrogen, 1s2, 2s2, 2p3, right? But then we add 3 electrons to it, and we get this. And here we have a magnesium ion, +2, which means it has lost 2 electrons. So neutral magnesium would be 1s2, 2s2, 2p6, 3s2. But when we lose them, these go away, and we get this. They all have the same electron configuration. That is isoelectronic. Okay, orbital notation. Orbitals, right? You can think about this as where the electrons live. And any one orbital can hold a maximum of 2 electrons. Each subshell has a certain number of orbitals associated with it. You can see it there. S has 1, P has 3, D 5, and F 7. Okay, now you might remember me talking about Hund's rule last year as kind of the public transportation rule, right? Where electrons will fill orbitals at the same energy level, right? Called degenerate orbitals, singly before pairing, right? Just like people riding public transportation will fill seats, right? Because there's always like 2 seats that are kind of right next to each other. They'll always fill those seats singly before having to pair up with, you know, that unsavory character who, you know, probably looks like me sitting somewhere, right? Guy with a beard, bunch of tattoos, probably giving you a dirty look when you come on the bus, right? You're not going to sit next to him if there's some place where you don't have to sit next to somebody. So think about this as the public transportation seating rule. These work exactly the same as electron configurations, right? We remember carbon's electron configuration, except that we now show the orbitals, right? These boxes with half arrows, or sometimes it'll just be a line with half arrows. So 1s, right, we've got 2 electrons, 1 up, 1 down, 2s, again 2 electrons, and then 2p, right? And p has 3 orbitals, and when we have our 2 electrons, we just draw our 1, 2, right? Because they're gonna fill those seats singly before having to pair up, right? Think something like oxygen, where you have one that pairs up because its electron configuration would be 1s2, 2s2, 2p4, right? So your 1s electrons, your 2s electrons, and then here, because we've got 3 orbitals but 4 electrons, they fill 1, 2, 3, and then the 4th one, just like that, because one of them is forced to sit next to that weird guy on the bus. So, things to remember: any orbital can only hold 2 electrons maximum. The block an element is found in on the periodic table always indicates where its last electron will be found, so the last term in the configuration. Electrons fill orbitals one at a time before pairing. Think about people on a bus. Electron configurations have only letters and numbers, while orbital notations have boxes or lines and arrows. All right, thanks. I will see you in class.